Okay, so this is lesson 4, in which we will deal with VSEPR theory and how to draw the VSEPR shapes, or how to define the VSEPR shape for molecular compounds. This will be the focus. Now, one thing that we'll start is, first of all, why is this name VSEPR? Okay, V stands for valence. Valence. S stands for shell. E stands for electron. P stands for pair. And R stands for repulsion. So what this theory is actually valence shell electron pair repulsion. Now, what we are doing here in chemistry 20 is that we are just scratching the valence shell electron pair repulsion theory, and we are not going into a lot of details on this. However, what we have to keep in mind is that the electron pairs will repel each other. Why repel? Because they are both negative charges. Therefore, based on the general law of charges, two opposite charges will attract, two same charges will repel. And those are two electrons, so the electron pair will repel each other. And in this case, what they will try to do is they will try to minimize their repulsion by maximizing the distance between the two. Why is this like this? If you will take physics 30, then you will know why is it, because the attraction or repulsion force, the interaction force between the two charges, is direct proportion of the charges, product of the charges, and indirect proportion to the square of the distance between the two charges. So if you are minimizing the repulsion force, that means that you will maximize the distance between those two forces. Now, in order to draw and to visualize the VSEPR diagram, we have to implement some rules. Okay, the first one is that single, double, triple bonds that we saw in the molecular compound are represented by one line only. So it doesn't matter if it is single or double or triple bonds, still will be one line. Lone pairs and bonding pairs are considered to be the same. So it doesn't really matter if you have a bonding pair or a lone pair, still they will have the same effect. The number of lone pairs around the central atom will determine will affect the VSEPR shape. So if we don't have any lone pairs, so then we'll have nothing to push it. Or if we have a lone pair, then those electrons that are in the bonding one and those that are lone pairs will try to repel each other. The other atoms are arranged so that the angle between electron pairs are evenly distributed. On the central atom. So when we see those atoms that are around the central atom, peripheral atoms that are around the central atom, the electrons and the forces that are between the two will create an angle so that the electron pairs will be evenly distributed. Okay, so now let's see and try to explain this table here. When we have a linear diatomic VSEPR shape, meaning that what we have is just two atoms in 180 degree between as an angle between the two. The number of bonding on central atom is not applicable. There is no central atom here. This is why. So this is not applicable. The lone pairs in the central atom, again, is not applicable because we don't have the central atom. The angle between that is formed in the linear diatomic shape is 180 degrees. The structural diagram in this case will be just 180 degrees, okay, between the two. So one here, an element A is here, and an element X is here. So we'll have A here and X here. They are connected between each other. The angle between the two is 180 degrees. Examples on this are all diatomic molecules like O2, H2, and so on, and things like HF. Okay. Linear triatomic, when we are talking about linear triatomic, then what do we have is that the number of bonds in the central atom is equal to 2. So we have central atom in this case, and the number of bonds on the central atom is 1 in one side and 1 on the other side. And we don't have any lone pairs in the central atom. So there is nothing to make it so that they will bend. Then again, this is a 180 degree between each other. And what is happening here is that we have a central atom as C, and then we have one atom here as A and one atom here as B. So the angle between it's again 180 degrees. Now let's see some general examples and some like real examples. So general one, what we will see will be an element A being the central atom and 2 elements on the other side of the central atom and no lone pairs. So examples of this will be, let's say, carbon dioxide. Okay. Now let's take a look at the other one, that is the triangular planar. What we have here is as the number of bonds in the central atom is 2. The number of bonds on central atom is 3. And there is no lone pairs, 0 lone pairs. The angle between the 3 is 120 degrees. And what do we have is something like this being the central atom. And then we'll have 1 here, 1 here, and 1 here. This 1, 1, 1. And the angle between those is 120 degrees. 20 degrees. Okay, now the general example of this will be a case when we have, let's say, A B3, B3, not B2, A, B3. A concrete example is, let's say, BCl3. And we know now that when we are drawing the structural diagram of boron, we will have zero lone pairs in the central atom because boron is satisfied with three electrons, 6 electrons in the outer shell. So the 3 chlorines will complete the outer shell. Okay. Now let's move to tetrahedral. This tetrahedral now is becoming a 3D shape, while all those ones that we saw here are in a plane. Okay, in a plane. While now tetrahedral will be, or trigonal pyramid will be in a 3D shape. So tetra means 4. Therefore, what we will see is we'll have one central atom and then 4 elements that is coming around it. So as the general form, this will be AB4, or as the proper example will be carbon CH4, or things like this. What you will see in terms of the shape is that you will see the central atom here, and then you will see 1, 2, 3, and 4. Okay. The angle between those will be about 107.5, 109 degrees. And what do we have in terms of the number of bonds in the central atom? Number of bonds in the central atom is 4, and the number of lone pairs is 0. When we move to the trigonal pyramid, the number of bonds in the central atom is 3, and then we have 1 lone pairs here. So what do we see in the trigonal pyramid is that we have angle of 107 degrees, and then what is happening here is that the general form of it will be, let's say, A, B, 2, E. Say E or C, doesn't really matter. And having the lone pairs here, then that means that those will push it. So you'll have 3 on the base, the central atom, and then you will have something that push it. So an example of this is NH3. Okay. And the diagram will be this. And you will have here the lone pairs that are in the making it as a triangular lone pair. And now the last one will be the bend, or the V shape, an angular V shape. And what do you have on the V shape is that you have 2 bonding, then you have 2 lone pairs, creating between each other an angle of 104.5. 104 is fine to state, and an example of it is like the general one will be something like water is the example for it, and then the structural diagram will be, here we have the central atom, and then we have one element here and one element here, and then we will have two lone pairs here, which will make it so that it's bent. And this angle here is 104.5 degrees. So in order to draw the VSEPR shape, what we have to do is we have to first draw the structural diagram of the compound, identify the number of bonds in the central atom and the number of lone pairs, and then based on this information we will see what it is. So on the case of phosphorus trichloride, what we will have is we will have 3 as bonds in the central atom and 1 lone pair, so therefore will be a trigonal pyramid. Trigonal pyramid. Well, before we move to the lab, I want to do more examples with you, and we will do this in class when we meet together. So please stop here, and we'll do more examples in class, and you can complete the lab, which will be a video in which you are showing me an example of a linear triatomic, linear diatomic, pyramidal, tetrahedral, and trigonal, and V-shape or bent or angular. Okay, this is today's lesson. You can complete the assignment after we do the examples in class so that you have a better idea of what it is, VSEPR shape, and how to draw it, how to approach